Today we're going to look over graphs and interpreting the graphs of functions and some key features of graphs. We should be able to tell the domain and range of a function from its graph and see if there are any features that we'll learn, like absolute maximums and minimums and things like that. So a little bit more vocabulary and then looking at graphs that we've looked at before in a new way to see what the graphs tell us. Roller coasters can be scary, but fun to ride. Below is the graph of the heights reached by the cars of the Thunderball roller coaster over its first 1,250 feet of track. The graph displays a function because each input value has one and only one output value. And you can see this visually using the vertical line test. Now, the vertical line test is a way to check graphs to see if they're functions or not. If you can draw a horizontal line, or not horizontal, a vertical line, and pretend that was straight, it only hits one spot on the graph, that is a function. Okay, no matter where I draw, it only hits the graph one time, that's a function. If it hit two times, it would not be a function. So if the graph was curved this way, and I hit let's see, the vertical line would hit it here and here, and that would be not a function if the graph was curved like that. But the way it is on this Thunderball roller coaster graph, it is a function because the vertical line test is passed. No matter where I draw a vertical line, it would only intersect it at one point. So now we need to look at this graph to determine the domain and the range. All right. Remember, the domain is all the independent variables. Okay, we might have to look at that definition in just a second. In this case, the distance along the track in feet. Okay. Domain is usually graphed along the horizontal or x-axis, and we can write the domain for this one from where it started, 0, to where it ended, 1250. And so the domain for all real values of x, for when we just have to make that little clarification, all real values of x, all the x values that are on this graph that make sense, 0 to 1250. You can't have negative track, so that wouldn't be a real value. -5, you can't have -5 feet of track. But from 0 to 1250, that is our domain. So x is in between 0 and 1250. We write it as an inequality to show that it's inclusive. It's got the less than or equal to signs on it to say it includes 0 all the way up to 1250 feet. So independent variables are the variables in which the input values can be substituted in a function. Basically, it's the variables that do not change. Okay, the track distance is always going to be 10 feet, 100 feet, 250 feet. Okay, that track is laid down, it's stable. It's independent of what we do. Our experiment is not going to be changing the track when we get our data. The change in the track is what affects the other variable, and that's going to be called dependent. That's going to be the range. How high above the ground is affected by where you are on the track. So it is dependent on this distance along the track, which is independent. That's just there. The dependent variable depends on something else, in this case, the distance. So the height goes from 10, starts off at 10 feet above the ground. You go up to 110, then you go down to 30, and then up to 90, and then down until it ends at 10. So the height, that's the height of the roller coaster. It goes up and down as you ride along the track. And so the distance, the range is from 10. Okay, that's where it starts from and ends from. That's the lowest point, 10. And it goes all the way up to 110. That's the highest point. That's our range from 10 to 110. And so we can write that as for all real values of y. 10 is less than or equal to y, which is less than or equal to 110. It's in between those two, just like we did when we did compound inequalities. We need it to represent the domain and range. Okay, the graph above shows that these data are continuous. It means there's no gaps in between the data. It goes from the starting to the end. Okay, continuous. They're all connected, indicating the domain are sets of real numbers with no breaks in between, no gaps. A graph of discrete data consists of endpoints that are not connected by a line or curve. Discrete data would be like this point, and this point, and this point if they were not connected by the lines. Many other useful pieces of information about a function can be determined by looking at its graph. The y-intercept, which is where it crosses the y-axis, it intercepts it, would be right here, 0, 10, y-intercept. The relative maximum is the greatest value for the function in that limited open domain. So the biggest value, the maximum, okay, like 110 would be the maximum from 10 to here. From 10 to here, okay? Biggest value is y equals 110. The minimum is the lowest value, okay? Maximum, biggest, lowest, minimum. Minimum is 10 right here. Now this is a minimum right here. It's just not the absolute minimum. It's a relative minimum. From here, like if you're just counting from 250 to 750, the minimum would be right here at 30. If you're counting from 0 to 1250, the minimum would be 10. Similarly with the maximum. The maximum from 10 to 1250 is 110, but the maximum from, let's say, 500 to 1000 would be here at 90. So that would be a relative maximum. Okay, that's just definitions we got to learn. Relative and absolute. Okay, relative is for the chunk you're looking at. Absolute is for all of the function combined. Same with relative minimum and absolute minimum. It's just if you're taking pieces of it or if you're taking the whole thing. And because they must occur within the open intervals, your relative minimums and maximum can't be the endpoints of the graph. So what is the y-intercept of the function shown in the graph, and what does it represent? All right, the y-intercept starts at 10, 0, 10. 0, 10. And what does it represent? It represents height at the starting point. Or the starting height. I'll just type it next time. Starting height. 0, 10. A relative maximum of the function represented by the graph. We've said that before. At 250, it's 110. So let's see. At 250, it's 110. Oh, 250, not 25. Hold on just a sec. Okay, you could have also said that it was also, or it could also, at 90. Okay, I'm just going to delete this one. Let's put 110, or it could be at 90. 250, 110, or let's say 800. It could be at 90, at 800. So 110 is a relative maximum, or 90 could also be a relative maximum. That's where they reach their highest points. Identify the absolute maximum. Now this is the absolute high, no matter where you're looking at it. That is 110. That's the highest track goes. Identify a relative minimum. Okay, all right, let's see. It said it couldn't be at endpoints, and so the relative minimum would be 30 at 5 or 550, but let's just put 30 for right now. 30 feet would be a relative minimum. Identify the absolute minimum. Okay. We would say 10 feet would be the absolute minimum. Remember, relative minimum can't be at the endpoints, but absolute can be. 10 feet would be the lowest that goes. What? The lowest height. All right, suppose you got on a roller coaster called Cougar Mountain that immediately started climbing the track in a linear fashion, as shown in this graph. Okay, remember, independent variable is the distance along the track, because that doesn't change. The track goes this long and stops. The dependent variable would be the height above ground, which does depend on where you are along the track. Okay, so let's identify the domain and range of this function. It goes from 0 to 200. That's the domain, the x coordinate, 0 to 200. And the range would be from 0 to, let's say, 175. 175 would be the range, 0 to 175. So domain 0 to 200, range 0 to 175. The y-intercept, where it crosses the y-axis, 0. Okay, 0. Remember, y-intercept, where it crosses the y-axis, 0. Identify the absolute maximum and the minimum of the function. Absolute maximum is 175. Absolute minimum is 0. Does it have any relative maximum or minimum? No, there's no relative, because it's all a continuous linear function. Okay, so it starts here, and that's the only minimum it's going to have. Then it ends here, and that's the only maximum it's going to have. And remember, that can't be at the endpoints, the relative. That was our definition. Way up here, relative maximums and minimums cannot be the endpoints, and that's all we have are endpoints that are relatively minimum and maximum. So number 9 is no, it does not. How are the extrema? Okay, extrema. You click on that, or you look up the definition on the side. All of the maximum and minimum of the extrema is where they're the extreme, the outer cases. So how are the extrema different on this linear graph versus the nonlinear? Okay, how are these endpoints, the extremes, the minimum and the maximum, different from here, the minimum, and here, the maximum? Well, you could say that there are no relative minimum and maximum values. That's how they're different. The nonlinear one did have relative minimum and maximum. It went up and went down. It went up a little bit and it went down more. This linear graph just goes from one point to the from the low point to the high point. There is no going back and forth. Number 11. This graph shows 5 points that make up the function h. Is the function continuous? So if I go from here to here to here to here to here, is that continuous Is it connected? No. Okay, no line connects them. It's discrete. There's a point here, and then there's a point here, and then there's a point here. This is a discrete graph. It's not connected. It's not continuous. There's no line from one point to the other showing that you include all those points. You only include the point here, then here, then here, here, here. Discrete, not continuous. Okay, 12. A function has three relative maximums, -2, 10.3, and 28. One of the relative maximums is also the absolute maximum. What is the absolute maximum? That's the biggest one. The absolute value maximum is 28. Tell whether each statement is sometimes, always, or never true. Okay, a relative minimum is also an absolute minimum. Sometimes, okay, not always, but sometimes. An absolute minimum is also a relative minimum. Sometimes, okay, remember, if it was at the endpoints, it can't be, but sometimes. Hold on just a second. So let's go ahead and review what we've seen so far. Okay, it's mostly a lot of definitions. Okay, vertical line test. If you can draw a vertical line up and down on a function graph, and it only intersects at one point, it passes the vertical line test and is a function. Okay, vertical line test. Independent variables. Okay, these are the variables for which the input values are substituted into a function. Okay, these are the input, the domain X input independent variables. Okay, usually the variables that are like the stable don't have anything to do with anything else. The distance along the track feet, it's always going to be this distance. Okay, the track is 1250. That's not changing. It's independent of what we're doing. Dependent variables does change. Okay, is the variable that does change based on the independent variable. The height above the ground it depends where along the distance along the track you are. Okay, so this is the independent one, the distance along the track. That doesn't change on anything. The independent variable, yes, the distance along the track is the independent variable. The dependent variable is the height above the ground on this graph, and it changes. It's the output, the range. It changes based on where you are along the deep independent variable. A lot of words that can get confusing. Independent and dependent. Just remember to read over these sections so that you can see definitions. Okay, we write them. Now we write our domain and range with compound inequalities. Since they're not discrete, which we'll go over in just a second, we don't write them as ordered pairs, okay, because it's an infinite range of them. There's an infinite number between 0 and 1250 if you count all the decimals and the infinite variations of decimals and fractions you can get in between each one. So we can't write all of them in the domain, so we need to say that it's from here to here using our compound inequality. Okay, continuous versus discrete. Continuous, the points are connected. It covers everything in between these points. Okay, from 0 to 250, 10 to 110. Everything in between is covered with this line. It's continuous. And from here to here and here to here, here to here, all of it is continuous because it's connected by lines. Discrete would look like this. Okay, this would be discrete. You have a point, then you have another point. Okay, then you have another point, then another, and then another. Discrete. It's separated by gaps. Continuous has a line connecting them. It covers everything in between. Okay, Y-intercept. Where it intercepts the y-axis. So think of like a football interception. Okay, it's caught. This is where the line is catching it, right here. at 10 on this graph. 0, 10. Let's see, on this graph, the intercept is at 0, 0, 0. Okay, 0. Where it intercepts the y-axis, the vertical axis, this one's called D and T, but the same as domain, range, x, y. Y-intercept, where it crosses, intersects it. Relative minimum and maximum, okay? Remember that they cannot correspond to the endpoints of the graphs. Relative minimum and maximums cannot be at the endpoints. They have to be in between, okay? Maximums are the heights, the tallest points. Minimums are the low points. And as long as it's not the endpoints, okay? Relative minimum and maximum. You have absolute minimum and maximum, which can be the endpoints, but is the absolutely the lowest and then absolutely the highest point. Absolutely highest right here, 110. Not this one, because there is a point higher than that, so that's not an absolute. It's a relative, but it's not absolute. And this one would be the absolute minimum, not this one, because this is the relative lowest one compared to where it is, but the absolute lowest one is at 10. Oh, no, over here, 10. They can be at endpoints. Absolute minimum and maximums can do endpoints. Let's see. I think most of the extrema is just maximum and minimum values. It's just a word for maximum and minimum, the extremes, sort of, if you just think of extrema. Okay, so make sure we look through all of these. Again, we got to be able to, we'll work on this again on the next lesson. It's just more graphs and seeing the same information that we've done with it today. You might want to try over here 6-1 practice 25 through 30, but it's just asking you to write the independent and dependent variables. Which of these is something that happens no matter what, and which one of them depends on what's been happening. Okay, usually in the same places as we've seen before. So notation, set notation to write the domain and range of the function. Remember your notation, we're using the compound inequalities like here and here to write using the set notation. You just put it in a curly bracket for all the real values of what we're talking about, the variable, and put the range in the domain. Identifying the minimum, absolute minimum, the absolutely lowest points on this graph. In this function, the absolute minimum corresponds to 2 points. What are the 2 points? Again, same thing. Where are the 2 lowest points on that graph? And what do they represent in context? That means if you're looking at this problem, okay, distance and time, what do these points mean? What are they saying? Okay, what points on the graph correspond to the absolute maximum? It's similar. Look for the highest point on the graph and think of the context. What does it mean about when we're talking about Tom's hike and the highest point over here? Read the variables to think, what are they talking about? Identify any relative or minimums or maximums. Find the y-intercept. Is it discrete or continuous? It's just some questions to see if you understand most of the vocabulary and how to read a graph.